keep working on whatever you're working on, labs and stuff, because this is kind of an open work period for the rest of class today. But just as some practice, as you're doing that, also take a look at these. See if you can figure out whether or not the reaction is a redox reaction in the first place. Might not be. And then if it is, what's the oxidizing agent? What's the reducing agent? That'll be a good review of what we just talked about before. Well, the overall charge is zero. The oxygen is oxidation states. Yeah. Right. Right. Yes. Right. All right, did you find some of these? Perhaps. Give me a couple more minutes. Did anybody find which one of these? There's one of these four that is not a redox reaction. Anybody see which one it is? B. Why is B not a redox reaction?
All of the charges, all the oxidation states are the same on one side.
Yeah, the oxidation states stay the same on both sides. So to see that, so let's look first at the right side. We've done H2SO4 before, but based on our list there, we know oxygen is going to be -2, and hydrogen is going to be +1. So that means sulfur must be what? No, because there's 4 oxygens, right? So that's -8 overall, and then +2. So that means we need 6 more. So that sulfur is going to be +6. Okay, over on the left side, we've done water before. Oxygen -2, hydrogen +1. So hydrogen and oxygen have not changed over oxidation state over the course of this reaction. You see that? Hydrogen stays +1, oxygen stays -2. So then let's look at SO3 and see if maybe sulfur has changed. Oxygen, based on our rules, has got to stay -2. So then what does sulfur have to be? +6. So you can see then that oxidation states do not change. Sulfur starts at +6, ends at +6. Oxygen starts at -2, ends at -2. Hydrogen starts at +1, ends at +1. Right, so no change there means not redox. The first one pretty obviously changes charge. Aluminum goes from 0 to +3. Silver goes from +1 to 0. The third one, barium goes from 0 to +2, and chlorine goes from 0 to -1. And then magnesium goes 0 to +2, and bromine goes 0 to -1. So in, let's just pick D, the last one. What is the oxidizing agent? Which is the oxidizing agent in D, the last one? Bromine. How do you know that? How do you know it's bromine?
Because first is 0 charge, and it goes to 1.
negative charge.
Right. So it's gained, it's taken electrons, it's oxidized something. You can think of oxidation as taking electrons away from something. So bromine has oxidized the magnesium, has taken its electrons away. All right. That's probably the biggest issue with these is getting those terms straight, making sure what is reduced versus what is the reducing agent. Those are two different things, usually opposite. All right. Do you feel okay about something like this? Maybe. There's some on the Mastering Chemistry to practice on that too. All right, let's take out this practice exam thing. And there's actually no redox on this one, I think. But I want you to start working through this. We've got a little over an hour left. So I don't know if we'll make it all the way through. But we'll stop. We'll stop in about 30 minutes and go see where everybody's at, and then go through what we've done so far. Specifically, if you want to skip some specifically good ones that you'll want to look at for the exam is 10. I'm sorry, that's 10 points. Number 4 specifically, make sure you can do that. And I would say 11, number 11. Make sure you can do that. And I mean, all of these are fair game, but those are some that we've specifically worked on those types of problems and that are going to be important. I also noticed that this particular practice, they must have done things in a little bit different order this semester. There's no naming here. And so that would be something that clearly will be on our exam, but is not on this one. All right, go ahead. You can also use this time to work on labs if you want. Whoops, but that's what we're doing now. Look through this, see what you're at, see what you need more work on before the exam next week. And we'll go through these. And I just realized I don't have a digital copy of that on this computer, so I have to go get one. I'll be back.
Add that value, how much zinc sulfate you use, and then subtract that from what you measured.
Yeah, we did that here. This and this.
That was your final. What was your final?
Yeah.
Yeah.
Yeah, but how do you do that?
So that's
You add this
that's
and
the
this. Yeah.
So you have to do this. Take that value and subtract it from
This.
There's always some questions.
See if it makes sense.
subtract that. When you measure it, with the our final mass crowd, our mass is all the different is 2.0.
This
That-
one, like,
that was when you subtracted.
oh, maybe I can
That did it, you did. This is after. No, but it's supposed to be between two numbers.
Oh, yeah. Yeah, so we don't need to subtract this.
I don't know where the hell.
The oh, no, because we zeroed it.
If you zero it,
Yeah, we zeroed
that's
it.
right. So you subtract, once you have them, you subtract.
Oh, we don't. We don't.
No, it's because we thought that we need to subtract the watch,
So this.
the weight. Yeah, no, that's right, that's right.
Right.
Yeah. Oh, no, that's not.
So this is just 2.
Yeah, yeah.
Yeah. Like you could.
For the access credit,
Well, for the it's all free.
this
Like you buy
this,
Yeah.
and this.
No, all this you have all the free ones.
Yeah, so the first thing.
Oh.
Yeah, that's what got you to
They make their money. Because if you get lots of pay money.
See, I don't get that part. I don't get the part that always saying the limiting reactant is this reactant and the access reactant is this one. Or we have the access, just the access.
Well, because how much of the excess revenue is left?
Over.
How the two.
So when
So your total value is the unit value of both of them together. So your total value is, okay, your total value, like the one you measured in the beginning, subtract the total and get excess revenue together.
yeah, I get that,
And that's
but
what it's
like in the questions, where is it? It's just asking, and they small big here and then so
say it's
Question. We're trying to finish this.
Yeah.
Lab, but we're confused because for this, if we have an unknown number, we don't know what the thing is, so we can't figure out what limiting reactant is because we don't know what we even used, right? Because it's an unknown.
calculated.
No, it's, the unknown is a mixture of the two. You just don't know what percentage of which one they are. Your tests show you the limiting reactant
That's what I'm confused. How does it show our limiting
from
reactant?
the results of this. After you made all the precipitate, one of them was still left over in the supernatant, the liquid. So when you test that liquid with one of them that makes it precipitate, that means that the other thing must still be stuck in the liquid. So one of them was all used up, the other one was still, some of it was
So
still
if we
liquid.
we measured the mass of what was left over.
Yeah.
How do we know what that leftover was? Like.
The mass of the precipitate is the product.
Yeah.
So you have the equation for the reaction.
Yeah.
Yeah. So the solid product, the solid precipitate, that's what you measured. That's what you formed.
Mm-hmm.
The leftover reactant is still in solution.
Okay. Let me go look at my notes.
Okay.
For question 6, it says the total mass of the excess reactant. Does that mean the total mass that was consumed or the total mass that was consumed and what was left over?
The questions are confusing.
The total mass of the excess reactant in the original mixture would be,
The amount consumed from the equation and then in addition the
right, I think that means the total mass, like both the excess and the stuff that was used
okay.
in the original mixture.
So there's no part here that they asked about finding the excess, like of the excess.
Just the amount of excess?
Well, you can
Yeah.
calculate that from the
Yeah, no, but is it
measured mass.
is
and
it-
then-
asked? Do we need to show that? Is it
Yeah,
not?
it doesn't really say that, but you'd need that information to answer this one, right? Because you need to know, the mass of the limiting reactant that was consumed. Oh yeah, and then you can just subtract to find the other one. So no,
Yeah.
it doesn't ask for specifically just how much was excess.
And then also, will finding products be on the test for equations, like the type of equations you talked about?
Yes, for the
Yes,
types of
okay,
equations I
because I
talked
didn't see
about,
it
yeah.
there. So
Let me, before I say that for sure, let me make sure that's in chapter 4. Yeah.
Okay. So this is a bigger one, right? So
Right.
So, you're saying here, determining limiting reactant, you add some
Right.
drops of that to
Mhm.
bigger one. Bigger one had, number 16, the number 16 thing, but we didn't know what number 16 is.
Wait,
Oh, okay, and then it's like.
that doesn't, what are the two different, you should only have one unknown.
See, but in the thing, you said there should be two unknowns.
Where?
You said, like, in the directions, you said take two unknowns.
No, you do one unknown, but you do it twice. You do two trials of that.
Mass two.
Yeah, two samples of the unknown solvents.
We did two different songs.
Okay, that's fine.
Two different songs.
You can tell you the average of those, but the two different, either one of the two should have been, should have been, you don't. So after the precipitate settled down, you took the eager and you got a little bit of the one, a little bit of the two,
So they are.
right?
I know, but unlike
No, we
the.
did two different ones. I think that was two different. That was two.
Right, but still. Yeah.
I think three minutes or like, I don't think
Because you're right, if you don't have that, then if you don't have that, then you can't figure it out.
I mean,
Oh, so you guys use it for the same problem? Okay. Yeah, because if you see the report, you have the report. Then she like questions stuff on it. Oh, is that here?
Yeah, it just really calls for the one unknown.
Yeah, that's why I was confused, because when we read the thing, it said like two unknown, and we read it as two unknown. Maybe that's
Yeah,
just a
that was
reading.
a
But so
mistake.
then, what do we do for this?
I don't know.
Should we use somebody else's data to do it?
No, I think you have to. Assuming that you wrote the stuff, because I was solid, you did it. It didn't seem like we were doing it wrong. You can still find it from your data. Because. All right, so for your first one, whatever, or you added some of this to group one, and you got away precipitation. So that means that your limiting reactant in that first sample was not this other one. That means there was leftover was this, right? Because that means there was leftover zinc sulfate, so you form precipitate.
Why would you say they
You put in sodium phosphate, and there was some zinc sulfate solution left over to react. And that was precipitate.
How does it sulfate?
Because we know the reaction. Think about the reaction. One chemical reaction is happening here. Sodium phosphate is reacting with zinc sulfate,
Let's study.
and making zinc phosphate, which is precipitate.
Doesn't matter what kind of salt it was.
No, they all have the same. They're all made of the same thing. It's just what the ratio is.
It's doing.
In that case, all the unknowns.
Well, the chemical reaction lab, when I did that, I did it in, I woke up and did it in the morning of.
See, I can't do that.
It's all made.
I should do that before, and it was creating.
Because like that night, all my friends were like, hey, let's have a fun.
The leftover ingredient.
Well, those were the spectator. The idea is that since these were not a stoichiometric mixture, after you did the original precipitation, there was left over, one of the reagents was left over in solution. The precipitate was the zinc phosphate. One of these two was left over in solution. So that leftover solution, you tested it, and you found that some added sodium phosphate is still precipitated. And that means that there was leftover zinc sulfate in solution.
So that means they solve it.
No, that was left over. Right. So then you can go back and do all the stoichiometric calculations, assuming that the other one was all used up. So that the amount of precipitate you recover, you can use that mass to go back and calculate how much of the limiting reactant was used.
Okay, start okay, so then can we just use the one that the data is over that already? Or
Yeah.
or-
Yeah.
But it doesn't equal to.
I don't know. No, it's not. It's not. Oh, you did it incorrect because which one is the final? Which one is your one?
This is our limiting.
Okay,
This is
so for the excess, you need to do this.
Sorry.
Okay. Well, for your excess reactant, what you do is you need to add whatever number you got from here, so you can equate two difference between this number and two of them.
The excess.
Yeah. So you need to do the excess left over from the reactant and the excess reactant.
Equals your.
Okay, so I bring this subtract. You know, so like, say you got excess, you got one, two. So the you got your total value is 1.9. Then for the excess reactant, 7 years two. I see. Oh. Minus 82. 31. So the excess is 72. 7 plus 31 over. Because this is how you use this. Right. Okay. You just calculate percentage of that, and then you go to the data, so whatever that leftover percent is, you just add it to that.
Oh, yeah.
Actually, I can just do either.
Yeah. Once I cut everything back to grams of carbon, grams of hydrogen,
Mhm.
I'm getting that actually to be the same exact number as that. Maybe I'm doing something wrong. So it doesn't give you how much.
No, that's correct, because there is only carbon and hydrogen in the
Oh, so it's not
in
CX.
xylene. It's a hydrocarbon. There's no oxygen in it.
Oh, I totally overlooked that.
Yeah.
I'm so used to doing the combustion as CXHYOZ.
Right. There's no oxygen now.
So it's not necessarily always going to be that formula.
Right.
Okay.
Good.
I think it's messing up between the two,
Mhm.
so I just want to make sure I understand what I'm looking for.
Okay.
So,
Oh, yeah.
so it says here, should I do this first or this first?
Yeah, and then we have.
They're the same thing.
They're the same thing.
I mean, basically, yeah.
So, okay, so if I'm determining the linear, I just did, so if we're taking only one,
Right.
so we did, here, when it said add one drops of this, or add one drops of that, equal to, what was that meant to?
It was meant to add that to the same thing, like
The
two
same
samples of the same thing.
So, it's
So one of them formed precipitate, and one doesn't.
so lucky for us that this
Right.
one did form precipitate.
Right.
Okay,
Every good weekend.
Very begin.
this one did, right?
Right.
That means that
I just like that.
zinc sulfate was what the supposed to be in that beaker too. It's supposed to be.
Well, that's what you're testing. There was some leftover reagent in that beaker. It was either sodium phosphate or zinc sulfate. So if it was sodium phosphate left over in the beaker, and you add more sodium phosphate to it, like in one, nothing would happen. But then if there was leftover sodium phosphate in the beaker and you added zinc sulfate to it, it would precipitate that leftover stuff.
That means that in this one it was Na3 plus zinc sulfate,
Right. Forms zinc
zinc phosphate, and then those other two.
And that tells you that there was leftover zinc sulfate in that beaker. Some self-precipitated form from it.
Because this was, wait, why would zinc, you said zinc sulfate would be left over?
Yeah, this was left over in the beaker. So that when we have this reaction.
So I thought sodium phosphate would be left over in the beaker.
So if you add sodium phosphate to more sodium phosphate, it precipitates. That doesn't really make sense, right? Just combine those two things to precipitate.
So then in this equation, it would have been left over, because this was a solid.
Right, that was the precipitating form of that sample.
Okay. And then for this one, zinc sulfate didn't react. Didn't
Right.
form a reaction.
That would tell you that the leftover one in that beaker was just more zinc sulfate. You didn't have both reagents present in the reaction.
Okay, so then if I'm checking for what the limiting reactant was, that's what fully reacted.
Right.
Everything did, so that would be this one.
Right.
And then PO4 because PO4 reacted to zinc. Is that why it's fully
Yeah.
reacted?
And you're on the right track. I mean, I'm not just going to tell you the answer. You got to think about it a little bit. But you're on the right track. Yeah. Think about how that would work and why doing that experiment shows that. That's what it's asking.
Okay, but this is the right formula in terms of.
Yeah. That's the way it works. Except for the stoichiometry is wrong.
Right, right.
PO4 should be CO3.
Okay.
Yeah.
Okay. Alright.
All right, we're going to go through the first few of these in a couple of minutes if you've had a chance to look at them. So we're working through this. No, we know, you know that it was a mixture of those two things. Sodium phosphate and zinc, or zinc, yeah, right. So the unknown part is how much of each one there was. That's what you gotta figure out. Yep, so you gotta write the chemical equation. Nope, no water. You've got, let's see, it tells you right here. There's your chemical equation, right? And so if you read through all this, it tells you exactly what's happening. So in this particular example, you had one where there was 200 grams of this and 120 grams of this. So you reacted it, you formed some precipitate, and then there's some excess reactant. So in this experiment, an unknown mixture of these two salts is added, and they react to form a precipitate. So depending on how much precipitate you got and which one was the limiting reactant, you can use that same technique that we've been doing with the stoichiometry to go back and calculate how much of each initial one you had. So,
Where can I turn this here?
wherever, yeah, just leave a pile. So the limiting reactant excess can be determined by the addition of solution of these to separate samples of the supernatant, which is a leftover liquid. If there's leftover of this stuff in that liquid, then adding more of this will make it precipitate. If there's leftover of this, then adding this will make it precipitate. So depending on which one caused to precipitate, that's how you can determine which one is limiting.
How do we know like how much of each we add to do this?
You don't, but you know how much precipitate you got at the end.
Okay.
So you use that to go backwards and calculate what the other ones were. All right, let's look at this one. So everybody, did you start from the beginning on this? Yeah? Okay, then we'll do that. So the graduated cylinder has this particular mass and contains a certain amount of water. A certain amount of metal is put on it and raises the volume by 52 milliliters, and the mass of the cylinder and its contents is whatever. So how do you go about determining the identity of this metal? What did you do? Yeah, the volume of the metal is the difference between where the water started and where it ended up. The volume of the metal is 10 mLs. And then how do you find the mass of the metal?
You have
Yeah.
the volume of water, and you have the volume of water, so you can solve the mass of the water.
It's true you can solve for the mass of the water. That doesn't really,
But then I took that,
that's not everything, right? Because
well, I took the mass of the cylinder plus the mass of the water in mine.
right,
112 times 2 degree.
right. So the mass of the metal is going to equal the total mass and then you've got to subtract the mass of the cylinder, and you have to subtract the mass of the water in the cylinder, which is 42 milliliters converted to grams, or 42.0 grams. And that comes out to something. $192 grams. So you got 192 grams divided by 10 milliliters is 19.2, which is gold. Make sense? All right. So now we're going to use these samples. Gives a sample of powdered metal to each 4 students, and they weigh the samples. The results of their multiple trials follow. The true value of the sample of metal is 8.72 grams. So who's the best at being both accurate and precise, and how would you figure that out?
The first person is,
How do you know?
because their average is 8.72.
Okay.
They're accurate, and then their range is the smallest among those who have.
Right. So you're going to judge accuracy by the proximity to the true value. So you'd have to calculate the average for each of those and see which one's closest to 8.72. And then your precision is going to be the range of the values. So which one has the smallest range is the most precise. So which one's the worst? What's the worst combination of accuracy and precision? Yeah. What do you think? 3? Why?
It's the least accurate and it's not really close to 8.72.
Never mind. Yeah, it's definitely far off, so it's certainly not accurate. But that one's actually quite precise in that they got the same value, or they got very close to the same value each time. They got a small grouping. So there's only a range of 0.03 difference in their 3 masses in number 3, even though it is way off. I think the worst combination of both is probably 4, right? Which has the average is the furthest off, and the range is quite broad, quite wide. Okay, let's look at 2A. How did you get the number of oxygen atoms in 0.05 moles of C3H8O3? I think there's only a couple people following along. Other people are working on labs, so go ahead and talk if you got it. Did anybody get this one? Yeah, how did you get it?
Since there's 3 oxygen molecules
Mhm.
in 1 molecule of this, that means that there's 3 moles for every 1 mole of this. So I multiplied the 0.050 by 3.
Yeah, so 0.050 moles of this, if we write the whole thing out here. And then we know that there are going to be 3 moles of oxygen atoms for every 1 mole of this molecule. And then it doesn't ask for moles of oxygen, it asks for a number of oxygen atoms. So we then have to multiply it by this to get atoms per mole. What did you come up with?
9.0 times
27. Wait, that's not right. Is it? Wait. Yeah, it should be much lower than that. Oh, no, that's right. That's right. Okay, I was thinking negative. Yeah, that's right. Yes. All right, let's skip down. Did anybody get to number 4 yet? Take a look at number 4 if you haven't had a chance to work it out yet. See if you can work this one out now, because this is a good example of one of these big kind of mole gram calculations involves limiting reactant as well. So it applies to like what you're doing in lab. Give yourself a few minutes to work this one out, and then we'll talk about it.
get the head centimeters squared. Right, and you can find this in centimeters cubed. What we have to do is divide it to get to this centimeters or 2 meters centimeters.
No,
So I look at this as base times height times
that's,
width.
well, that's an area.
Base times height.
That's an area. And this is a volume. So, you're trying to find thickness. You're trying to find that extra, height or however you want to call it,
Yeah.
width. So you have to do that by using this as the mass. Right?
So yeah, I've always thought of
And then, yeah, so ounces is the mass, fluid ounces is volume, ounces is mass. See, you can use it here. So you convert that to grams, then you use that to get use that with this to get the volume. This times, yeah. Yeah, so that's right, so then you divide this by
Divide
area, you get the.
Oh, that's what I
Yeah,
was asking.
you're right, okay.
Also, in I don't know which assignment it was, but Mr. Chemistry, but this is the head.
That's the same, it's a different stone.
I was just making sure.
I don't know if they have on here. Yeah, they use the AE on here too.
That's lower.
I've seen it both ways. All right, do you have number 10 down? Has anybody finished this one? 4? It says 10 points. I keep getting confused. How many people have finished this one? Anybody working on it that needs a couple more minutes on it? Yeah, okay. Give it a couple more minutes.
This is a makeshift periodic table. We're actually supposed to compare to the actual one.
I think that's a, like, if that were the periodic table.
Okay. Next, it's kind of confused. It's like there is no three.
Right.
Three periods here.
All right, can we go through this one now? Starting to get a little low on time, so I just want to make sure we get through it. Okay. We've got silicon carbide, and here is its equation. Another thing that we might say, since this class clearly didn't deal with naming, when we do a problem like this on our exam, you can expect that it's a possibility that the equation would not be given. That it simply says silicon carbide is made by heating silicon dioxide and carbon to high temperatures and also performing carbon dioxide. I would give you the formula for silicon carbide because we hadn't talked about that. But anyway, you should be able to come up with formulas for silicon dioxide, carbon dioxide, carbon, it's just C, and then write down and balance an equation for that. All right, so now that we have that, how many grams of silicon carbide can form when 4.5 grams of silicon dioxide and 3 grams of carbon are allowed to react? So we have to do what first? We've got our balanced equation, so what's next? Yeah, we got to get moles, and that's how we're going to be able to compare to see about a limiting reactant. So we're given the molar masses, which is helpful. That means we're going to take 4.5 grams of SiO2 divided by 60.09 0.749 moles of silicon dioxide and 0.250 moles of carbon. Okay. So how do we determine which one is the limiting reactant? Because we can't even answer A yet until we find the limiting reactant, right? Because we don't know which one to base our calculation for the product off of. So how do we find the limiting reactant? You can do one of two ways, right? You pick whichever reagent you want, calculate how much of the other one you need, and then compare if you have more or less of that one. So let's do that. We'll just start with this SiO2 because that's what I wrote down first. Multiply that by what we see in the equation, which is 3 moles of carbon for every 1 mole SiO2. And that tells us that we need 2.25 moles. Whoops. No, that's not right. 0.225 moles of carbon. And how much do we actually have of carbon? We actually have 0.250 moles. So does that represent an excess then, or less than what we need? It's an excess, then it's more than what we need. So which one's limiting? The SiO2 must be limiting because we have what we need of the other one. We have more than what we need of the other one. So that means that's what we're going to use to determine the answer to A. We're going to use that number to calculate the amount of silicon carbide that can form. That's 1-to-1, so we don't really even need to put in a thing there because we can see from the equation that one of these reacts to make one of these. So 1/1 is 1. Then we can just So I'll put 1/1 just so we know where we've got it there. And then we can convert that back to grams, which is we're given that 40.10 grams per mole. And what do you come up with? Can we get down? Good? Yeah. 3.00 grams of silicon carbide. So that's how much you'd get. And then how much of the excess reactant would remain? 0.03 grams? Oh, grams. Sorry. It doesn't say, that would be moles, yeah. It doesn't specify that, but I guess we should make that in grams. So the excess is going to be, since we need 0.225 moles, we have 0.250 moles. So the excess is 0.025 moles of carbon. Which, yeah, is about 0.300. So you'd have 0.300 grams of carbon left over. So, is that what you got? Does that work? Okay, great. Okay, let's look down at, this is kind of an interesting question. I don't know how far you've gotten here. Well, I guess I'll ask you then, so those of you who are working on this, which one you want to go over next? Do you have any troubles with any of them? Not sure whether you got it or not? I'll leave that to you. Number 11, sure. All right, so the aluminum package containing 75 square feet of foil weighs approximately 24 ounces. Aluminum's density is given here. What's the thickness of the aluminum foil in millimeters? So we've got some aluminum foil here that is probably going to be pretty thin, but has a thickness nonetheless. We know it's 75 square feet. We don't know anything about the width or any of the other measurements. But we want to know what that thickness is. That's what we're trying to figure out. So let's see if we can figure it out. We know how much it weighs. We've got 24 ounces of aluminum foil. So if we know the weight, we know we can get the density. And then we know the area as well. So if you've got the area and you've got the density, you can get the height, right? Area, if you think about units, area is square centimeters or square feet, square centimeters. Volume is cubic centimeters. So if you have the two of those, that's like saying the area times the thickness gives you the volume. So the area, which is length times width, times the thickness, which we might consider as the height, if it were just a cube, is the volume. We want all these units to be the same, so we want the area in cubic centimeters. The thickness, this is going to be our unknown, and then our volume is going to be in cubic centimeters. So we know the volume, although we know it we will know the volume when we get it from the density. We know the area, but we'll have to convert units, and then we should be able to figure out the thickness from those. So let's go through and see if we can do that. First thing probably, well, it doesn't matter what you do first. We have to convert the area from cubic feet or from square feet to square centimeters, and we have to get volume from mass and density. So I guess let's work on volume first. Doesn't matter, but is that okay? You want to do that one first? Okay. So the volume of our aluminum, we're going to get by looking at the density and the mass. 24 ounces, and then we're told that an ounce is 28.4 grams. So that's going to get us from ounces to grams. And then we're going to use the density to get volume. The density, we're told, is 2.70 grams per cubic centimeter. So that's 24 times 28.4 divided by 2.70, which is 252. I guess if we're being careful about significant figures, there's only 2, but I don't know. We'll just stick with that for now. That's fine. So that's cubic centimeters or milliliters. That's the volume of the amount of aluminum. You see where that comes from? Okay. So now, remember, in order to find the thickness, we need the volume and we need the area. We've got the volume, and we're told the area, 75 square feet, but we don't want it in square feet. We want it in square centimeters. This is always a tricky conversion because of the square. So you've got, let me show you what I mean by that. So you've got 75 feet squared. If we multiply that by 1 inch over 2.54 centimeters, oh wait, that's inches anyway. So we got to get from square feet to square inches first, I guess. So if we go from 12 inches per foot, like that, notice that those units don't cancel out. Feet squared cancels with feet, and so now we have inches per foot, or inch over foot, which is not helpful, right? Or sorry, we have foot inches is what would be the product if we just did this. So what do we have to do to get the full conversion? You got to do it again, because you have to, if you think about an area like a square or something, you have to convert the length, we'll say, 2 centimeters, and you have to convert the width. So you have to get both of them. Make sure that little 2 doesn't get forgotten up there. And you have to do this twice. So 75 times 12 times 12 is 10,000. Yeah, have a good one. Oops, square inches. 10,800 square inches. So be careful with these compound units, squares and cubes, that you're accounting for all of them. All right. Now that we've got square inches, now we can put that into square centimeters, and we still have to be careful. We could have done this all in one big line if you like, but I didn't. So we're going to do the same thing here. 2.54 centimeters per inch and 2.54 centimeters per inch. The other way to do this, if you prefer, is to make your own conversion factor by squaring this. So take 2.54 squared, and that's how many square centimeters per square inch. So now I've got 69,000, we'll just say 700 square centimeters. Okay, so now we have volume. Let's write that down. 252 cubic centimeters. And we have area, 69,700 square centimeters. So to get thickness, we need to divide 252 by 69,700. So that equals 252 divided by 69,700. And I get 0.00362 centimeters. Does that sound good so far? Is that about what you got? Those of you who got through it? All right. Now we're not quite done because the question asks for what's the thickness in millimeters. Be careful with those questions, especially the multiple choice ones. So you will have some multiple choice questions on the exam that are like this, but there's just one answer that you have to pick. You got to make sure that you're picking the one in the correct units that are being asked for. One thing that you'll see on the exams as the semester goes on, we'll have 2 exams and then the final. So between the 2 exams, the multiple choice portion will increase a little bit because the final is a national standardized exam and that's all 100% multiple choice. So to prepare for that, we'll do that. In a problem like this, you know, if you forget to convert to millimeters on a 10-point question, you might lose a point or something. But on a multiple choice question, you lose them all if that's the issue. So let's make sure to do that. We can hopefully by now kind of do that by sight, move the decimal over 3 places, and see that that is 3.62 millimeters. Oh, centimeters, you're right. I thought it was meters, so I'm totally wrong. Yeah. So we got to just move the decimal over once, right? One spot. Thank you. So that should be 0.0362 millimeters. I was thinking meters. So I would have gotten the multiple choice question wrong even after my big speech there. All right, I guess we'll stop there. Keep working through this. We'll come back to it on Monday or Tuesday. And probably Monday, because then we're going to have a quiz on Tuesday. And then happy studying for the exam on Wednesday.